Subscribe to Dr. Khalkar's classroom channel and press the bell icon to get latest updates. In my previous video lecture, I have discussed about introduction of optic fiber, important parameters of optic fibers, propagation of light inside the optic fiber, and important equations for it. In this video, I am going to explain optic fiber part 2. So let's get started. The content of this video are types of optical fiber, attenuation and reasons of losses in optic fiber, optical fiber communication system, pros and cons of optical fiber, and several applications of optical fiber. Let's see types of optic fiber. According to number of modes, there are two types of optic fiber. First is single mode fiber, abbreviated as SMF. Second one is multi-mode fiber, abbreviated as MMF. Next is according to refractive index. Again, there are two types. First is step index fiber, abbreviated as SIF, and second one is graded index fiber, abbreviated as GIF. So let's see all one by one in detail. In single mode fiber, the core size of single mode fiber is very small. It is the diameter is typically around 8 to 12 micrometers, and only single mode, that is zero order, can travel through it. As shown in diagram, the typical diameter is around 125 micrometer for the optic fiber, whereas the core diameter is nearly 10 micrometer. This is index of refraction, where n is a mode of transmission of the signal. This is optic fiber cable with core having refractive index n1, whereas for the cladding the refractive index is n2. In single mode fiber, the input signal and the output signal is shown over here. It shows that both these signals are almost similar, so there is no any modification is observed. Now let's see next type of optic fiber, that is multimode fiber, abbreviated as MMF. The multimode fibers propagate more than one mode. The number of modes propagated depends on the core size and numerical aperture. Typical value of fiber core size are 50 to 200 micrometer. In this diagram, the diameter of core is 200 micrometer, whereas diameter of cable is 380 micrometer is shown. This is index of refraction, where n is mode number. N1 and N2 are refractive indices of core and cladding respectively, as shown in this optic fiber. In multimode fiber, the input and output signals are shown with the propagation of light in the form of signal. Optical fibers used commonly in telecommunication applications have size around 125 micrometer, and refractive indices are N1 is equal to 1.5 and N2 is equal to N1 into 1 minus delta, where delta is equal to 0.01 to 0.02 value. Next type of optic fiber according to the refractive index is a step index fiber, abbreviated as SIF. In step index fibers, the refractive index of the core is uniform and undergoes an abrupt change at the core cladding boundary. In single index fiber, light rays entering at different angles of incidence with the axis travel different path lengths and emerge out at different times. This results in pulse dispersion, that is, the input pulse gets broadened as it travels along the fiber. So as shown in this diagram, the diameter is around 200 micrometer for the core, whereas 380 micrometer for the cable. This is index of refraction, and this is the propagation of the light rays in the optic fiber. This is the input signal and this is output signal, where there is a abrupt change is observed. Next type of optic fiber is graded index fiber, abbreviated as GIF. In graded index fibers, the refractive index of the core varies gradually as a function of radial distance from the fiber center. Here, as shown in diagram, the diameter of the core is around 50 to 100 micrometer, whereas the diameter of the cable is around 125 micrometer. This is index of refraction. The ray is continuously bent and travels a periodic path along the axis as shown in this diagram. The rays entering at different angles follow different paths with the same period both in space and time. This results into periodic self-focusing of the rays as shown in figure. Therefore, the pulse dispersion is less as compared to the step index fiber. So here input and output signals are shown. Now let's see what is the core cladding index difference. In practical step index fibers, the core with radius has a refractive index N1, and for cladding, refractive index is N2. A typical value of N1 is 1.48. The cladding surrounding the core has a refractive index slightly lower than N1. The relation between N1 and N2 is shown in this equation, where N2 is equal to N1 in bracket 1 minus delta, where delta is called core cladding index difference or index difference simply. The value of N2 are chosen so that the index difference delta is equal to 0.01. So this equation is very important to design optical fiber cables which are used in telecommunication systems. So this is all about the types of optic fiber cables. Now next important parameter is attenuation. Attenuation in fiber optics, also known as a transmission loss, is the reduction in intensity of light beam or the signal with respect to distance traveled through a transmission medium. Attenuation is the loss of optical power as light travels along the fiber, caused by several mechanisms including absorption, scattering, geometric effects, and bending losses, etc. Signal attenuation is defined as the ratio of optical input power, that is Pi, to the optical output power, P0. The following equation defines signal attenuation as a unit of length. So attenuation alpha is equal to 10 upon capital L log to the base 10 Pi upon P0, where capital L is the length of the optic fiber, where Pi is the input power and P0 is the output power. Now let's see the types of attenuation. There are main two important types. One is intrinsic attenuation and extrinsic attenuation. In intrinsic attenuation, there are again two types. One is absorption by materials, that is absorption loss, and second one is relic scattering, that is scattering loss. In extrinsic attenuation, that is macro bend loss and micro bend loss. So let's see all these four one by one. First is absorption loss. Material absorption occurs as a result of imperfection and impurities in the fiber, which results approximately 3 to 5% of attenuation. The most common impurity is the hydroxyl OH- molecule, which remains a residue despite stringent manufacturing techniques. The hydroxyl may be present due to water remnants that enter the fiber optic cable material through either a chemical reaction in manufacturing process or as humidity in the environment. The natural impurities in the glass absorbs the light signal and convert it into vibrational energy or some other form of energy. The hydroxyl radical ions and transition metals such as copper, nickel, chromium, manganese, etc. have electronic absorption in and visible part of spectrum. Their presence caused heavy losses. Next is scattering loss. Relic scattering results the majority, about 96% attenuation in optic fiber. The local microscopic density variations in glass cause local variations in refractive index. These variations, which are inherent in manufacturing process and cannot illuminated, acts as abstractions and scatter light in all directions as shown in this figure. Relic scattering showing attenuation of an incident stream of photons due to localized variation in refractive index. This is known as relic scattering. Relic scattering is greatly depends on wavelength. It varies as 1 by lambda raised to 4 and becomes important at lower wavelengths. Thus, Rayleigh scattering gets lower limit on the wavelengths that can be transmitted by glass fiber at 0.8 micrometer, below which the scattering loss is very high. The extrinsic attenuation is caused by two external mechanisms, macro bending and micro bending. Both of them caused reduction in optical energy. So let's see. First of all, macro bend loss. Macro bend loss, it is a large scale bend which is visible when fiber is bent through a large angle. Strain is placed on the fiber along the region that is bent. The bending strain will affect the refractive index and the critical angle of the light ray in that specific area. As a result, light traveling in the core can refract out and loss occurs as shown in this figure. Next is microbend loss. It is a small scale distortion. It is localized and generally are small microscopic bends of the fiber axis that occurs mainly when a fiber is cabled. Such bends occurs due to external forces, uneven coating applications, and improper cabling procedures. Microbending might be related to temperature, tensile stress, or crushing force. The structural variation in the fiber or fiber deformation cause radiation of light away from the fiber as shown in this figure. Light rays get scattered at the small bends and escape into the cladding. Such losses are called as microbend losses. Let's see the attenuation plot. A typical plot of fiber attenuation versus wavelength for silica-based optical fiber is shown in this graph. It shows peaks corresponds to Rayleigh scattering, OH absorption, UV absorption, and infrared absorption. For better performance, the wavelength must be on minimizing loss and minimizing dispersion. Such windows are selected for communication purposes. It is seen from attenuation curve that it has minimum at around a particular band of optical wavelengths. The band of wavelengths at which attenuation is minimum is called optical window or transmission window or low loss window. There are three principal windows. This corresponds to the wavelength regions in which attenuation is low and matched to the capability of transmitter to generate light and receiver to carry out detection. So according to this table, wavelength between 820 to 880 nanometer, the dB per kilometer is 2.2, whereas in 1200 to 1320 wavelength nanometer, the dB per kilometer is 6, whereas for wavelength 1550 to 1610 nanometer, the dB per kilometer is 0.2. From above data, it is seen that 1550 to 1610 nanometer is most preferable from the point of view of dispersion. The low intramodal dispersion wavelength about 1300 nanometer is most suitable. This is all about the attenuation plot. Now let's see the attenuation due to dispersion. Dispersion is phenomena related to variation in velocity of different wavelengths or different modes. Dispersion losses are the result of distortion of optical signal when traveling along the fiber. The light wave spreads as a function of time when it propagates. Due to pulse broadening and overlapping, the output signal gets distorted. Intermodal dispersion is there. A ray of light launched into the fiber follows a zigzag path. When many modes are propagating, they travel with different net velocities and come out at different times, which cause broadening of pulse. The low numerical aperture fiber exhibits smaller dispersion. Also, narrow spectral width of source limits the dispersion. Next is waveguide dispersion. The effective refractive index for any mode varies with wavelength, which cause pulse spreading. This is waveguide dispersion. Next one is material dispersion. It is based on the wavelength of optical signal. Light waves with different wavelengths travel at different speeds in a vacuum. The short wavelength waves travel slower than the long wavelength wave. Thus, material dispersion can be reduced using monochromatic light source. Therefore, hence laser light is very much suitable for optic fiber communication. These are important parameters which are responsible for the attenuation due to dispersion. The attenuation due to dispersion is shown in these figures where input and output signals are shown. The input signal which carry the information in the form of light, which includes zeros and ones. The same signal as the output of the fiber is shown, which contains the same information but signal strength is reduced due to attenuation. During propagation, signal gets mixed and distortion will occur in the output signal, which shows composite pattern in which zero is missing. This is the graphical representation of attenuation due to dispersion. Now let's see one of very important application of optic fiber is optical fiber communication system, which includes three important parts that are transmitter, optic fiber cable and receiver. Let's see in detail one by one. So in transmitter side, first is message origin. Generally, message origin is from a transducer that converts a non-electrical message into an electrical signal. Second one is modulator. The modulator has two main functions. It converts the electrical message into proper format. It impresses this signal onto the wave generated by the carrier source. Two distinct categories of modulation are used, that is analog modulation and digital modulation. Third one is carrier source. Carrier source generates the wave on which the information is transmitted. This wave is called the carrier. For fiber optic system, a laser diode or a light emitting diode is used. They can be called as optic oscillators. They provide stable single frequency waves with sufficient power of long distance propagation. Next is channel coupler. Coupler feeds the power into information channel for an atmospheric optic system. The channel coupler is a lens used for collimating the light emitted by the source and directing this light towards the receiver. The coupler must efficiently transfer the modulated light beam from the source to the optic fiber. So all these blocks are in transmitted side where the signal gets transmitted. So this is the first important part. Second important part is information channel, that is optic fiber cable. The information channel is the path between the transmitted and the receiver. The fiber optic communications, optical fiber is the channel. A signal propagating along a fiber normally contains a range of fiber optic frequencies and devices. Its power along several ray paths. Now the third part is receiver, in which first block is optical detector. The information being transmitted is detected by detector. In the fiber system, the optic wave is converted into an electrical current by a photodetector. The current developed by the detector is proportional to the power in the incident optic wave. Detector output current contains the transmitted information. This detector output is then filtered to remove the constant bias and then amplified. Next is signal processing and amplification. It includes filtering amplification. Proper filtering or maximizes the ratio of signal to unwanted power. Next is message output. The electrical form of the message emerging from the signal processor are transformed into a sound wave or visual image. Sometimes these signals are directly usable when computers or other machines are connected through a fiber system. So this is all about the optical fiber communication and its detail about all these three parts, that is transmitter, optical fiber cable and receiver. Now let's see the advantages of fiber optic communication or conventional methods. First is high data carrying capacity. Optical fiber can carry very high frequencies, nearly 10 raised to 14 Hz, which are helpful in carrying more information, that is more phone lines or more TV programs or more data or internet, etc. As optical fibers are thinner, more fibers can be bundled together for increasing data carrying capacity. Next one is high quality signal transmission. Signals from one optic fiber do not interfere with those of other optic fibers, which do not degrade the signal quality. No leakage of information is possible due to this. The signal degradation is very negligible as compared to the conventional copper wires. The optic fibers are made from dielectric material which provides isolation between transmitter and receiver. Next one is no noise or no stray signal mixing. As optic fibers are made up of either glass or plastic, they do not pick up a stray signal or noise like copper wire does, either due to transmitted signal or due to external factors like environmental effects. Thus, the effect of external electromagnetic interference, lightning, external magnetic field, nuclear radiation is very minimal. Next one is cost effective. Optical fibers are typically made from silica. They are very cost effective as they are manufactured in bulk mass production. Next one is a small size, lightweight and flexible. Optic fibers are small in size, lightweight and are flexible. Due to this advantage, they are very helpful in medical imaging, in endoscopes, laparoscopes and mechanical imaging. Inspecting mechanical welds in pipes and engines in airplane, rockets, space shuttle, etc. Next advantage is less power consumption. Optical fiber consumes less power for its operation as compared to the metal wires. Next one is high tolerance and corrosion resistant. Optic fibers can tolerate extreme temperature variation, in some cases even up to 800 degrees Celsius. Corrosion due to water or chemicals is very minimum for optic fibers, or even it is negligible. Next one is ideal for carrying digital data or digital signal. Optical fibers are very much suitable for carrying digital signals that are ideally suited for computer networks. As large amount of data can be transmitted, they are very useful in broadband internet, LAN connection, etc. So these are all advantages of optical fiber cable. Now let's see the cons of optical fiber, that is disadvantages of it. It needs more expensive optical transistors and receivers. Installation and maintenance require expertise. It is slow to make any sort of network. Unidirectional light propagation is required for the optic fibers, and it cannot transmit electricity. So the signal is transmitted with the help of light only. It is delicate structure, very fragile, so handle with care is needed, and its cost is high. So these are the main disadvantages of optic fiber. Let's see the applications of optic fiber in other fields. Optic fiber cables find many uses in a wide variety of industries and applications. Some uses of optical fiber cables are included medical. In medical field, it is used as light guides, imaging tools, and also a laser for surgeries. Next one is defense or government, used as hydrophones for seismic waves and sonar, as wiring in aircraft, submarines and other vehicles, and also for field network. Next one is data storage, which is used for data transmission. Next one is telecommunications. Fiber is laid and used for transmitting and receiving the purposes. So it is very important role in telecommunication. Next one is networking. It is used to connect users and servers in a variety of network settings and help increase the speed of accuracy of data transmission. So very important role in data transmission. Next one is industrial or commercial. It is used for imaging in hard to reach areas, as wiring as sensory devices to make temperature, pressure, other measurements, and as wiring in automobiles and in industrial settings. So this is very important part. Next one is broadcast or CATV. Broadcast or cable companies are used fiber optics cable for wiring, CATV, HDTV, internet, video on demand and other applications. So as far as optic fiber is concerned, there are several fields in which optic fiber is used. Now here are some pictures of optical fiber cable installation. This is all about types of optical fiber, attenuation and reasons for losses in optical fiber communication system, advantages and disadvantages of optical fiber, and applications of optical fiber in several fields. In next lecture video, I will discuss about problem solving on unit number 2. So please don't miss it. Thank you. Below this video, in the description, the link of important information related to this video is given. Please go through it. Please like and share this video and subscribe to Dr. Khalkar's Classroom channel to get the notifications about my upcoming videos. Thank you.